This is section 10.4, and in this section we're going to be talking about polar graphs. So in the last section we talked about how to plot points and convert those points to and from polar form. So now we're going to move into polar equations. Now we can graph these using several methods. One is we can convert that polar equation to a rectangular equation and then graph it. This is not always easy. Right? It's not always a pretty rectangular equation, and it's not always easy to even convert it. We can plot points. You recall when you started graphing lines that was one of the things that we did. We just plotted some points, played connect the dots. We can use symmetry. That's something we really haven't talked about a lot for a while now. We talked about things like even functions and odd functions back when we were doing the first chapter that we did. And so we talked about things being an even function being symmetric about the y-axis and odd functions being symmetric about the origin. So we can certainly use symmetry here. We can use a calculator or some kind of computer algebra system. A computer algebra system is something like any of the kind of programs like Maple or MATLAB or any of those kind of more sophisticated graphing applications. So let's start off with plotting some points, because that's like one of the easier ways of doing this. So if we want to graph r equals 4 sine theta, so I went ahead and just wrote out all of this. You can see there's a whole lot of it happening here. I just picked a bunch of angles for theta. And you can see I kind of went in, so I went in 45-degree increments, and then I was like, oh, that wasn't enough. So I kind of went back and got, a couple others in there. By plugging in those angles and then taking 4 times the sine of that angle, I got all of these values. Now, remember, when you go to plot these, you're plotting these in polar form. So of course I've got this polar grid that I'm graphing everything on. Okay? And what I did was I kind of drew those lines out there so that I had those 45-degree markers in each one of the quadrants. So my first point here is 0, 0, right? R theta, so right there on the pole. Then we have this 2.8 and 45 degrees. That means if you go out along the 45-degree angle, 2.8 units, that's about 3. So that's that point right there. And then 90 degrees had an R value of 4. That means on this 90-degree angle right here, we went up 4 units. That's 4 of those concentric circles. And then so on. So I really, so here's what happened. I got to 180 and I was back at 0. And then I did 225. And so 225 was down here and it gave me negative 2.8. So look, I'm right back over here. So all of these right here, the 225, 270, 315, all of those ended up being unnecessary because those ended up being repetition. So that's why I went back and did the 30 and the 60. So that I could get, this 30 and the 60, I could kind of get that shape. So the blue is me just kind of connecting the dots here for what's happening. Now, let's look at that equation. So this polar equation, r equals 4 sine theta, you might recall from the last section when we converted these to rectangular form. I multiply both sides by r to give me an r squared and to give me that r sine theta. That r squared we know is the same as x squared plus y squared. And we know that r sine theta is the same thing as y. So we end up with this rectangular equation. Now, if I move that 4y over, this is the equation of a circle, right? So if I complete the square and stuff, so I just kind of zip through that a little bit, you can see that we get this center is at 0, 2 and a radius of 2. So this is a circle. That's kind of messy, and if you don't recognize that that's a circle or remember how to complete the square, all that stuff, yeah, that gets really messy. And that was a nice one. So when they get a lot worse, it's this is going to be, you know, almost unusable. Okay, so we're not going to be really been using this method of this plotting points. But what we are going to use is symmetry and our calculator. All right? So recall that we were able to test for symmetry about the x-axis, y-axis, and origin back in college algebra. Okay, that was in the rectangular equations. So you might remember, if you remember that you can like replace x with negative x and y with negative y and things like that. The polar symmetries are very similar. So we have three types of polar symmetries. Right? We have symmetry about the polar axis. Remember, the polar axis is similar to what we know as the x-axis. If you replace theta with negative theta and the equation remains the same, then the graph will be symmetric about the polar axis. The second type of symmetry is about the line theta equals pi over 2. That's what we think of as the y-axis. Here, if you replace r and theta with negative r and negative theta, and the equation's the same, then you got that symmetry. Lastly, we have symmetry about the pole, or the origin. If you replace r with negative r and the equation's the same, then you get that symmetry about the pole. So let's look back at example 1 and let's test that equation for the three types of symmetry. So let's go back to r equals 4 sine theta. So first one, polar axis. For that symmetry, we're going to replace theta with negative theta. So here's my original equation, r equals 4 sine theta. So notice I replaced theta with negative theta. What you're going to do with these is make use of those even and odd functions. So we know that sine's an odd function. So we have sine of negative theta, we remember is the same as negative sine theta. So that negative can come out. This equation is not the same as the original. Now, here's the thing about these symmetry tests. If the symmetry test results in the same equation, then the graph is absolutely symmetric about that, you know, in this case it would be the polar axis. If the equations are not the same, then, sorry, I was going to write something and that changed my mind. If they're not the same, then you don't know anything. That the test is then inconclusive. Okay? So if the test results in a different equation, the graph may or may not have that symmetry. So basically, yes means yes and no means maybe. So it means that you know nothing. The test is inconclusive. Okay? So let's do the second symmetry test. The second symmetry test is about the line theta equals pi over 2. Remember, that's kind of the y-axis. Here we have to replace r and theta with negative r and negative theta. Going back to the original equation was r equals 4 sine theta. So you can see in red how I changed r to negative r and theta to negative theta. Now if I do that, this becomes, you know, just stays negative r. Remember how sine was an odd function? That means that the sine of negative theta is negative sine theta, so that negative comes out front. This time, though, we can divide both sides by negative 1, and look, we get the exact same equation as the original. So we're guaranteed symmetry about the line theta equals pi over 2. Lastly, symmetry about the pole, that's the origin. For that one, we're going to replace r with negative r. That's because we know if it's symmetric about the pole, you can kind of think of that as a diagonal kind of symmetry, to where the r values are opposites there. So going back to my original equation, r equals 4 sine theta, and now I'm going to change that r to negative r. All right, well, that's not the same. Really, how are they going to end up being the same? Well, they're going to end up being the same if you end up with like 2 negatives and you can divide them out, or maybe like in the case of the cosine function, you know, how it's an even function. So if this were cosine negative theta, that'd be the same as cosine theta. So in cases like that, that's kind of where the, you know, you're going to get those cases where the equation is going to remain unchanged. So because this is not the same, we may or may not have symmetry. Remember, the test is inconclusive. So here's what we know. We know for sure that it's symmetric about the line theta equals pi over 2. The others, we don't know anything about. So let's look back at the thing here. This is a circle, so just like close your eyes and squint and just pretend that that blue thing's a circle. It kind of looks all pointy and stuff, but pretend it's a circle. It is absolutely symmetric about that line theta equals pi over 2, right? That's what that line is right here. Right? It's nice and symmetric about that. It's not symmetric about the origin, nor is it symmetric about the polar axis. So yeah, in this case, those maybes were actually no's, but you know, we can tell by looking at this. So what you would do then is, you know, get out your calculator to graph that r equals 4 sine theta. And we're going to do that in the next part of the section. So that concludes the first part for section 10.4.